Well, hi there, sports fans. Welcome to another exciting edition of Physics 12. Today we're looking at lesson 5.6, which is on orbital potential energy. So we'll see what that's all about. So we've come across the concept of potential energy before, and it's given by that expression there, mgh. And that is true anywhere on the surface of the Earth. So we can use that expression mgh anywhere where we are on the surface of the Earth, and that's because the distance to the center of the Earth is pretty much the same anywhere that you are on the surface of the Earth. It varies a little bit, well, a little bit. On top of a mountain, you might be at 9,000 meters or something like that. But that's not a huge deal when we're talking about potential energy. That's still going to work with this expression right here. However, once we get way up there, like if we get into outer space, even a couple of hundred kilometers above the surface of the Earth, this does not work anymore. Why is that? That's because the force of gravity is significantly different when you get a couple of hundred kilometers away from the surface of the Earth. So we can't use that anymore, so we have another expression which we have to use. And when we get way up there, then we need to use this one here, which is minus g m1 m2 over r. Again, r being the distance from the object, which is in outer space somewhere, to the center of the Earth or the planet that you're talking about. So, potential energy then, again, is given by minus. Notice there's a minus sign here, and I know you might be wondering, why is that? It is a little difficult to wrap your mind around a negative potential energy. How can you have negative potential energy? The reason is that we have arbitrarily said that out at infinity, so an infinite distance away from the center of a planet, the potential energy is 0. So out at infinity, potential energy is 0. So that being the case then, if you're out here at infinity and you're coming closer to this particular planet, whatever it might be, the potential energy has to decrease. So as you get closer and closer to an object with a force of gravity, your potential energy decreases. Again, if you go back to mgh, when the height increases, in other words, if you move away from the surface, potential energy increases. So if you're moving toward the planet, then potential energy has to decrease. And so if you're starting at 0 and you're going to go down from there, the only way to go is into negative numbers. And that's probably the best explanation I can give to you. It is a little bit more complicated than that. However, we'll just leave it at that. So if you're going to start at 0 and you're going to go down, the only way you can go is into negative numbers. So that's why we have a minus sign in front of the expression, so potential energy has to be 0. And so with the expression, here it is right here again, it'll be negative g m1 m2 over r. And notice it's r, it's not r squared. Alright, so don't get that confused with the force of gravity, which is r squared. So potential energy is negative, and it's just r, not r squared in the denominator. Now, kinetic energy is the same. It's still 1/2 mv squared. So potential energy, when we're talking outer space, is minus g m1 m2 over r. Kinetic energy stays the same, 1/2 mv squared. So here's a typical kind of a problem with orbital potential energy. So we have a 2,900 kilogram space probe. It's 3.8 times 10 to the 5 meters from the center of the planet. And they give you the potential energy, which is minus 1.7 times 10 to the minus 11 joules. Then what is the mass of the planet? Well, so if we write down the information that we have, so we've got potential energy in joules here, and then there's our expression for potential energy. The mass of the probe is 2,900 kilograms, and the distance from the center to the planet that the space probe is 3.8 times 10 to the 5 meters. So we want to find m2, and sorry, m2 should be over here. I didn't put that on there. So we will now. So m2 is what we're trying to find, which will make the mass of the planet. And if we put all of our numbers in and we figured out correctly, we punch it into our calculators correctly, we should get 3.3 times 10 to the 23rd kilograms for the mass of that particular planet. I'll just put M2 again over here so I don't forget later. Alright, so fairly simple, straightforward kind of a question, and that gets us our answer. So the only thing we didn't know was M2. So M2 is the mass of the planet, and again it's 3.3 times 10 to the third kilograms. Okay, so that takes care of part A. Then part B. If the probe falls to the planet with a speed of 6.2 times 10 to the third meters per second, then what's the radius of the planet? So here what we need to do is we need to use the work energy equation, and this involves the conservation of energy. We'll assume the space probe is at rest when it starts to fall. So when it hits the surface, it's then at 6.2 times 10 to the third meters per second. That's its speed when it hits the surface of the planet. So it starts at rest, and this is its speed just before impact. So we'll put the other numbers in that we have. We have M1, which is the mass of the probe, is 2,900 kilograms. And we have, we figured out M2, calculated M2, which is the mass of the planet that it's falling toward, and that's 3.3 times 10 to the 23rd kilograms. And it started out at 3.8 times 10 to the 5th meters, so that's R1. And so we're going to make use of our work energy equation again. Now, we can simplify this a little bit because the only forces that are working here is the force of gravity. So the work added to the system, or energy added to the system, is going to be 0. And again, if we expand on our equation, the initial kinetic energy plus the potential energy has to equal the final kinetic energy plus the final potential energy. But we can simplify that a little bit too, because we said the probe was at rest initially, so the initial kinetic energy is going to be 0. So here's how it's going to look. Potential energy initial equals kinetic energy final plus potential energy final. So here is the formulas that it's going to look like. So there's initial potential energy, that has to equal kinetic energy plus the final potential energy. So there is our equation there. So now we just have to put the numbers in where they're supposed to go. So that will look something like, oh, and R2 is what we're trying to find, right? So we have everything else here. We have numbers for everything else in this entire equation except for R2. R2 is what we're trying to find, which is the radius of the planet. So when you put all your numbers in, you get one big mess. Well, no, you need a fair bit of paper here, but that's what it's going to look like. So here's initial potential energy, there's kinetic energy, and then this just extends. I didn't have enough room on the other side there, so I just put it over here. And here is the final potential energy, and R2 is what we want to find. Now, I'm not going to go through all the steps of solving or getting to your answer. I assume that you can do the math, do the arithmetic here, and solve for R2. And so when you do, you get R2 equals 2.9 times 10 to the 5th meters. So here's a typical, this is actually a fairly straightforward kind of a question. And this is making use of potential energy when you're above the surface of the Earth or another planet. And it makes use of the conservation of energy as well. And don't forget that potential energy is negative when we get above the surface of the Earth or significantly above the surface of the Earth. Kinetic energy is the same though, 1/2 mv squared. And again, just follow all your steps, and if you just follow, just trust the equations and put the numbers in where they should go, and you should have a lot of success with these kinds of problems.